Okay. At some point, I'm going to say we're actually doing statistics in this class. It's starting pretty close to now. And that's because we're starting to talk about things statisticians talk about. Confidence intervals is something they talk about. And so let's talk about it ourselves. So here's an example of the procedure you might go through in order to figure out how to best present information collected from a sample, and trying to figure out the population proportion by using the sample proportion. So we'll make a confidence interval for the population proportion using the sample proportion, and we'll follow along with this example along with the general stuff that goes with it and see how that goes. So we start off with a sample of 500 voters and ask that they support legalizing pot for the whole of the U.S. 500 is not a very big number. And suppose we get 234 said yes and 266 said no. We'd like to know the proportion of all voters, but all we have is this sample. So a good place to start and try to analyze the proportion would be to compute the sample proportion. The sample proportion is just the number of yeses divided by the sample size. And so about 46.8% of the sample would be in support of legalizing pot for the whole U.S. That number is called the point estimate, and it would vary. It would vary from sample to sample. So if we did it again, I'm not going to get 234 and 266. I'll get maybe something close. We know a little bit about that, how that varies, because we know a little bit about now how the sample proportion works, because we know its sampling distribution. We'll worry about that in a second. Adding and subtracting a quantity called the margin of error to this number gives an interval likely to contain the true population proportion P. P represents the true proportion, P hat represents the proportion computed from the sample. To find this margin of error, we start with the sampling distribution of P hat. So here's what it looks like. So we're happy. Well, it's approximately normally distributed. We're happy about that. It's centered on the true value. We're quite happy about that. And so we look at the kinds of values that are close to the true value, where we get most of the values. So most of the time, we're at least this close, whatever that distance is. P hat's at least that close. Oh, that close. So it says 95% of the time, P hat is within, my hand's not cooperating, 1.96 times sigma of P. We'll just keep that in mind. We go, why are we using 1.96? I thought we've been using 2 all this time. But that was just for convenience. The exact number that you can get off the normal tables to capture 95% of the, for Z. So if you do Z like this, it's 1.96 and minus 1.96. That is exactly 95%. So in general terms, if you take the mean and you go 1.96 standard deviations away from the mean on each side, and you look at that region, so here we go, these kinds of P hats, from P minus 1.96 sigma to P 1 plus 1.96 sigma, captures 95% of the P hat values. So that says 95% of the time P hat is within 1.96 of P. And so we can use that to say, well, that means, so P hat 1.96 sigma plus or minus 1.96 sigma captures P for 95% of the P hats. And that's the notion here of the confidence interval, that we take this idea here and we turn it into something where we have an interval that we know that in 95% of samples, that interval is big enough that it reaches out from this estimate far enough on each side that the true proportion is likely to be in the interval. And we'll continue on this way of thinking on the next slide. Here we go.